And the 2-qubit error rates on IonTraps are much larger, much higher error rates. But I guess another interesting thing that's here, that you can see from here is just the, you can't really see it from here, but sort of where the error is coming from. So in some devices like superconducting qubits, a lot of the error just comes from the time it takes to do an operation. So if you can do the same operation faster, you have less error. And that's different from IonTraps, because IonTraps, when an ion's sitting there, there is no noise essentially. So it doesn't matter if you do usual operations faster or slower, it's not going to affect the noise on that gate.
So IonTraps also have like low spectator noise.
Low spectator?
Spectator noise?
What is that?
Like noise due to qubits that aren't participating in the computation.
So noise on the resting qubits?
Yeah.
Yeah, I mean, in principle, the noise should be very, very low on the resting qubits, which is not true for superconducting qubits. So in superconducting qubits, whether you're doing something interesting or not, there's noise accumulating all the time. Right. Maybe even more interesting table is done here. Here. So we'll get to these slides later, but this is just another table that sort of does a little bit of comparison. And so what these guys did is they considered different kinds of algorithms. So this is supposed to represent an algorithm. And what we have here is this gives you the fraction of gates that are used in the algorithm. So 37% of the gates apparently are Hadamard gates, and this whatever they're doing factoring or something. 14% are CNOT gates, and 46% are 1-qubit T gates. So it's 14% are two qubit gates. These are all 1-qubit gates, and these are all preparation measurement, all 1-qubit operations. Okay, and then they encode. So they took this circuit and they figured out how to encode this into error correcting codes, and that changes the composition of the gates. And then they compared this in 3 different architectures: neutral, optical lattice, or superconducting qubits, or IonTraps. And the big difference here is, so big difference is they're saying the noise rate is much lower for IonTraps versus superconducting qubits, but to trade that off, the gate speed is much faster here versus here. And they actually they try to look at all the details and figure out like the actual execution time from this architecture versus this architecture for some algorithm. So this is 10 hours, and that's 2 years. They have to use a different number of qubits. So like here, for this operation, it takes 5 years versus 50 days. That's the difference. And the number of qubits here is 10 to the 12 versus 10 to the 5. And that's because the error rate is much higher for these superconducting qubits, and so you need a larger overhead to deal with that noise than for the IonTraps. You can explain this more later, but people have looked into this, done all these kinds of comparisons. Yeah.
So how do we define the probability of the error?
Yeah. Okay. So let's go on. Let's try to dig deeper into this. So here's let me just talk about noise a little bit, and then we can talk about our model for the noise and whether our model is right or wrong. Okay. So noise. There's different kinds of noise. One is global noise, another is local noise. So global noise is like Armageddon. There's nothing you can do. So if somebody wipes out your whole quantum computer, like you can't do anything. It's gone. Okay. But local noise is more interesting. So local noise says, I mean, there's different kinds of models of local noise, but the easiest one is that every individual qubit is evolving on its own. So there's some noise on the individual qubits when it's sitting on itself. But if this qubit's sitting here and this qubit's sitting here, and there's no correlated noise between this qubit and that qubit. So the only time, in the strictest possible model, the only time there's correlated noise between 2 qubits is when they're supposed to interact with each other. So you can turn on that interaction yourselves and turn it off yourself. So if you turn it off, you only have 1 qubit noise acting independently. If you turn on, then there's more. And this is an extreme case. You can also imagine sort of local noise models where like there's some geometry, like the qubits are laid out in a plane, and noise affects nearby qubits. So there's correlated errors between nearby qubits, but not between distant qubits, just because that's sort of how physics works. Right, so this is called a local noise model. Right. And in principle, I mean, with this kind of model, when you apply a CNOT gate, the actual operation that's being applied is a 2-qubit channel. So it's represented by some cross-operator representation. And I suppose you can always, since the CNOT gate, the ideal CNOT gate is a unitary, you can always pull that off. I mean, you can put one CNOT gate into here and pull off another. And so you can think of what's happening is whenever you apply physical CNOT gate, what actually happens is a perfect CNOT gate is applied, and then some channel is applied. And hopefully this channel is close to the identity channel. And so the strength of the noise would be some measure of how close this is to the identity channel. There's different measures. Okay, and so the reason we're hopeful is this, which is that we're smart. We can apply interesting coordinated operations to this quantum computer, whereas nature is stupid. Nature is only acting locally, and so we can try to defeat nature by creating interesting correlations that catch the kinds of errors that are introduced independently. Versus global noise, which we can't do anything about. I mean, if there's some correlated noise between all these qubits, I mean, there's not really that much you can do about it, unless it had a very special form. Okay, so different kinds of noise. Typically, okay, so there's errors. Okay, so there's different ways you could divide it up. So one is memory error. So memory error just means if you have a qubit that's sitting there, what happens as time passes? Ideally, the identity channel, but possibly not the identity channel. Okay, and so what could be happening, for example, is it could be that this qubit has a certain lifetime. One can imagine. So, for example, if it's a photon, then it could be that it's absorbed or it disappears after a certain amount of time, and that's just a stochastic process. So over every nanosecond, you have a probability P of losing this photon. So that would be a stochastic noise process. There's other noise processes which are like you're supposed to have the identity channel, but in fact it's rotating very slowly. So there's some magnetic field or something that's rotating the qubit slowly, and that would be I don't know, on a short time scale, that would be like a systematic noise, because if the magnetic field is constant, then it's always rotating at the same rate, and so you can hope to do something to cancel it out, or to deal with that, and so that's the difference between like systematic errors and stochastic errors. So a stochastic error is something that's just random. It happens or it doesn't happen with some stochastic probabilities. A systematic error is one that's always there, and moreover, it's always the same. So, like for example, if when you try to do a CNOT gate, you actually apply a controlled Z gate, and every single time that you get the same error, that would be a systematic error.
Aren't you just applying a control Z gate?
Yeah. Yeah. No, I mean a more typical example is when you try to apply an X gate, which is a pi rotation on the black sphere about the x-axis. Maybe you actually apply a pi times 1 plus epsilon.
Oh.
So you over-rotate by...
So you always over-rotate by 1.
Perhaps, yeah, because like you've misjudged the frequency by some epsilon amount. So you're always going for slightly too far. So that would be a systematic error, and you could hope to do something interesting with that. And I don't know, a lot of the time as a theorist, you like to pretend that systematic noise won't happen, because if you knew that some noise was there, and it's always the same, then why don't you fix it? Right? the experimentalist should fix it until it's not there anymore, and then you only have to worry about the stochastic things that happen randomly. I mean, in practice, this isn't really the case. I think, the systematic error rates are quite high, and part of it's because of calibration, I guess, because they drift out of calibration, or I don't know.
So the systematic error that you're saying, like which sort of rotates the block vector like at constant speed, there are like tricks that they can cancel it out, like applying some echo pulses and that
Yeah,
sort of
exactly.
cancel
Yeah,
it out.
yeah.
Which they do actually.
Yeah.
It's not that they are not.
No, yeah, sure. Yeah, and like they don't do this, like they don't do a pulse sequence like this in order to do the gate. They do something
Yeah.
slightly more sophisticated, or in fact, they do a more sophisticated sequence of pulses in order to cancel out these kinds of errors. Yeah, so like a 1 plus epsilon kind of error hopefully would not happen. But they do have other kinds of errors. And I think actually, I think they do have other kinds of systematic errors, and it's just like they don't actually know what they are. So that like I'm not sure, like they can tell it's systematic, so you get the same error, but they don't know where it's coming from or how to fix it. So it's not that easy. Also, so stochastic versus coherent. So stochastic is, again, with probably P something interesting happen. Coherent is more like the error is unitary by over-rotating or something. So for stochastic errors, you need to have density matrices if you want to understand them. For coherent errors, you can just use a pure state to understand it, because it's just a unitary on pure state. Other things. All right, so Markovian versus non-Markovian. All right, so this is just another distinction. So Markovian is the same as like a Markov chain. So a Markov chain, the interesting thing about a Markov chain is that the probability of going to the next state only depends on your current state, not on the past. So it's memoryless. So Markov means he doesn't have memory. And noise, ideally we think of, hopefully our noise is going to be Markovian, but in fact that doesn't have to be the case, because like there could be that there's qubits in the environment that are just sitting there, and your quantum information like could be swapped out into that environmental, into the environmental qubit. Then an hour later that could be swapped back, and so the qubit comes back. And so these events, and there's correlations between what's happening in your system between now and an hour later, because the environment's been sitting around holding this information for that long time. And that's generally very, very bad, because it's hard to understand. So usually we hope that the noise model is going to be Markovian. So if information is lost into the environment, then hopefully that information is really lost, and it just disperses out into the wider environment as fast as possible, because we don't want to come back and mess us up. That's this distinction. Right. I don't think I can explain this, because we haven't talked about Hamiltonians. Right. So this is supposed to be, it's a differential equation that gives you the time evolution of a system, where part of it is unitary coming from the Hamiltonian, and part of it comes from these Lindblad operators, which is these, assuming that the environment is Markovian, meaning that you can trace out the environment every dt after very small amounts of time. Then you get a nice clean differential equation that gives you the evolution of the system. If you have a non-Markovian system, there's no hope for a clean differential equation, because you just have, you have to keep track of more dimensions. But here, the interesting thing here is in a Markovian system, you only need to keep track of the number of degrees of freedom you need to keep track of is just the density matrix of your system. You don't need to track the whole environment or anything to understand it.
So in the non-Markovian case, you'd have to keep track of the environment dimensions.
Yeah, which usually we won't understand, so it's probably hopeless.